Transition metals. General properties of transition metals. Transition metals are when ions are formed with incomplete d subshell. Characteristics of transition metals are complex formation, color ions formed, variable oxidation states, and catalytic activity. Zinc is not a transition metals because it forms +2 ions, which has a completely filled d subshell, so doesn't have partially filled d subshell. Complex formation. Complex is a central metal ion with ligand surrounding it. Ligand is an atom, ion, or molecule that donates lone pair of electrons. Coordinate bonds in complex formation, and this is when shared pair of electrons in covalent bonds are from one bonded atom. Coordination number is the number of coordinate bonds formed with metal ion. Ligands are monodentate, so only form one coordinate bond per ligand. Ligands can also be bidentate, so can form 2 coordinate bonds per ligand. Ligands can be multidentate, so form multiple bonds per ligand. Substitution reactions. Water, ammonia, and chloride ions are monodentate. Ammonia and water are similar in size and uncharged. Chloride ions are larger in size and have a 1- charge. Ammonia and water can be exchanged, but coordination number doesn't change. Substitution may not be complete like for copper, which will have 4 ammonia and 2 water, and this is deep blue color. Reactions with chloride ions. Adding high concentration of chloride ions to aqueous ions is a ligand substitution reaction. The copper with 4 chlorides is a yellow-green color. The cobalt with 4 chlorides is blue. Chloride ions on a transition metal forms a square planar, and this can change coordination number from 6 if they're water or ammonia to 4 with chloride ions. Solid transition metal chloride dissolved in water forms an aqueous transition metals water complex. Bidentate ligands. Ligands can be bidentate, so the ligand has 2 lone pairs of electrons, so 2 coordinate bonds form per ligand. Example is ethane, 1,2-diamine. 3 bidentate ligands used, and each one bonds to ion twice. It had coordination number of 6 and forms octahedral shape and bond angle of 90 degrees. Example is ethanidiote. This has 6 for coordination number, forms octahedral with bond angle of 90 degrees. Partial substitution happens when the ligand needed to substitute other ligand is dilute, so can't be used. It can only substitute some ligands and not all. Multidentate ligands. An example is EDTA 4-, which forms 6 coordinate bonds for each ligand. Shape and book. Heme is iron 2+ with multidentate ligand. Oxygen forms coordinate bond with iron, so oxygen can be transported around the body. Carbon monoxide is toxic to humans because it forms a stronger coordinate bond with hemoglobin than oxygen does. Stability of complexes. Substitution of monodentate ligands with a bidentate or multidentate ligand means a more stable complex if formed, and this is called chelate effect. Chelate effect explained based on positive entropy change in reactions, as there are more molecules of products than reactants. So, if a copper had 6 waters to form the complex ion, and you added EDTA to form copper with EDTA and 6 water molecules, then the copper complex ion has changed from monodentate to a multidentate ligand. So, increase in entropy because there are more moles on product side than reactants went from 2 to 7, creating more disorder. Gibbs free energy is negative, and enthalpy is small and entropy is positive. EDTA used in river to get rid of poisonous heavy metal ions because EDTA complexes are not toxic. It's in shampoos to get rid of calcium ions in hard water, so can be lathered. Even when bidentate ligand used to substitute monodentate ligands, there's an increase in entropy because of increase in moles from 4 to 7 in reaction, and entropy is positive. Enthalpy change being close to 0, the number of dative covalent and type are the same, so energy needed to break and make bonds is the same. So, Gibbs free energy is negative and complex formed is stable. EDTA titrations. Formation of a stable complex between EDTA and metal ions are measured by a quantitative titration when a suitable indicator is used. Shapes of complex ions. Transition metal ions normally form octahedral complexes with small ligands like water and ammonia. Transition metals ions can form tetrahedral complexes with larger ligands like chloride ions. Square planar complexes are also formed like cisplatin. Linear shape is silver ion, which forms two coordinate bonds with ammonia, and this is Tollens reagent. Isomerism in complex ions. Complexes have two types of stereoisomerism, which is cis-trans isomerism and optical isomerism. Cis-trans isomerism in square planar complexes. Cis forms C and trans is a positive. Cis and trans isomers for square planar. Cis and trans isomers for octahedral. Remember, optical isomers are mirror images of each other that are non-superimposable. Formation of colored ions. Color changes are from changes in oxidation state, coordination number, and ligands. How color arises. Ligands cause energy levels of d orbitals to split. Portion of visible light is absorbed to excite a d electron. Light that is not absorbed is transmitted to give colored substance. Ligands cause 5d orbitals to split to 2 higher energy orbitals and 3 lower energy orbitals. Electrons excited from 3 orbitals to the 2 orbitals. Energy difference of the split orbitals equal Planck's constant, which is 6.63 multiplied by 10 to the power of minus 34 multiped by frequency in seconds or hertz. Energy difference of the split orbitals equal Planck's constant, which is 6.63 multiplied by 10 to the power of minus 34 multiped by speed of light, which is 3 multiplied by 10 to the power of 8 divided by wavelength in meters. Solution is blue if it absorbs orange light. Energy split in d orbitals energy gap will be equal to frequency of orange light multiplied by Planck's constant. Energy of the blue solution equals Planck's constant multiplied by frequency. Changing color. Changing ligand or changing coordination number changes energy split between d orbital, changing the energy gap, which changes the frequency of light absorbed. Compounds without color. Scandium is part of d block, and its ion doesn't have electrons in d subshell to move around, so no electrons move between d block orbitals and can't absorb visible light. Zinc 2 plus ions and copper plus ions, the d shell is full, so electrons can't move into the other half of the d subshell orbital, so can absorb visible light. Spectrophotometry. Visible light passed through sample of colored complex ions. Some of the light is absorbed. Amount of light absorbed is proportional to concentration of absorbing species and to distance traveled through solution. Some complexes are pale and don't absorb light that strongly, so ligand is added to intensify the color. Absorption of visible light used in spectrometry to find concentration of colored ions. Spectrometers have colored filter. Color of filter chose to allow wavelength of light through that would be strongly absorbed by colored solution. Method: add ligand to intensity color. Make up solution of known concentration. Measure absorption or transmission. Plot graph of absorption against concentration and measure absorption of unknown and compare. Variable oxidation states. Transition elements have variable oxidation states. When transition metals form ions, they lose 4s electrons before 3d. Redox potential of transition metal ion changes from high to low oxidation state based on pH and ligand. The trends are relative stability of +2 state and can be +3 states. Compounds with high oxidation state are oxidizing agents, and compounds with low oxidation state are reducing agents. Vanadium has 4 oxidation states. Ion with V at +5 oxidation state is a solid compound, which is an NH4VO3, and it's got a string oxidizing agent. Adding acid to solid turns it into yellow solution. Zinc metals acid is reducing agent that reduces transition metals ions from high oxidation to lower oxidation states. Zinc added to vanadium in its acidic state will reduce vanadium's oxidation state, and color changes from yellow to blue to green and violet. Silver with 2 ammonias attached to it is Tollens reagent and used to find out what's aldehyde and what's ketone. Aldehydes reduce silver in Tollens reagent to silver. Catalysis. Catalysis increases rate of reaction without being used up by giving an alternative pathway with a lower activation energy. Transition metals and their compounds act as heterogeneous and homogeneous catalysts. Heterogeneous is in different phase from reactant. Homogeneous are in the same phase or reactants. Heterogenous catalysis. Heterogeneous catalysts are normally solids and reactants are gaseous or solutions. Reaction happens at surface of catalyst. Adsorption of reactant at active site on surface leads to catalytic action. Active site is where reactants adsorb on surface of catalyst. So, bonds or reactants become weak, or molecule held in come reactive configuration. Higher concentration of reactants at solid surface, so higher collision frequency. Strength of adsorption lets us know how effective catalytic activity is. Some metals like W have too strong adsorption, so products aren't released. And then there's metals like silver, which have weak adsorption and reactants don't adsorb in high concentration. Transition metals use 3d and 4s electrons of atoms on metal surface to form weak bonds to reactants. Surface area increases of solid catalyst will improve effectiveness. Support medium maximizes surface area and minimizes cyst-like catalytic converters. Steps to heterogeneous catalysis. 1. Reactants form bonds with atoms at active sites on surface of catalyst. 2. So, bonds and reactants are weakened and break. 3. New bonds form between reactant close together on catalyst surface. 4. This weakens bonds between product and catalyst, and product so desorbs. V2O5 used in contact process. Cr2O3 catalyst used in manufacture of methanol from carbon dioxide and hydrogen. Iron used as catalyst in Haber process. Nitrogen and hydrogen, which form ammonia. Poisoning catalyst is when impurities, and this reduces efficiency. Poisoning has impact on cost, and lead poisons catalytic converter. Homogeneous catalysis. When the reactant and catalysts are in the same phase, the reaction carries on with an intermediate species. Intermediate has different oxidation state compared to original metal, and at the end of the reaction, the original oxidation state will happen. This shows the need for variable oxidation state in metal catalysts. Transition metals have variable oxidation states because they can gain or lose electrons, so are oxidized or reduced because of the partially filled D subshell. Example is reaction between iodide and persulfate ions. Uncatalyzed reaction is very slow because it needs collisions between two negative charged ions, and because they're like charges, repulsion will affect this, so the activation energy will be high. Homogeneous catalysts need an electrode potential in the middle of the other two electrode potentials. So, it will oxidize reactant with more positive electrode potential and reduce reactant with more negative electrode potential, and now they will have lower activation energies because the ions are able to collide and react with each other. Catalysts having electrode potential between the two metals doesn't mean it's the catalyst needed, because it doesn't show that rate of reaction will increase. Iron 3+ could be the catalyst, because both steps in catalyzed reaction can happen in any order. Example of reaction is autocatalysis between inthanediote and manganate ions. Autocatalysis is when product of a reaction catalyses the reaction. Slow initial uncatalyzed reaction because the negative charge ions repel each other, so there's a high activation energy. After this, the manganate ions produced acts as autocatalyst and speeds up rate of reaction by creating an alternative path with lower activation energy. Slows down when MnO4- concentration decreases. Remove sample and titrate to find concentration of MnO4- ions, or use spectrometer for measurement of how intense the purple color is. This means that reaction rate is determined faster and reaction mixture is not disturbed. Constructing catalyzed mechanism for reaction. This is catalyzed by cobalt-2+ ions in acidic solution, sulfur trioxide ions, and oxygen forming sulfate ions. Split full equation into its two half equations. Add cobalt to make the two new equations, so oxidized cobalt equation is combined with original reduced half equation. Check mechanisms equations and add original, full, non-catalyzed equation. Silver chemistry. Silver plus ion form linear complexes with water and ammonia. Silver is like a transition metal where it forms complexes and shows catalytic behavior, but it absorbs too weakly. Silver not like transition metals, as it doesn't form colored compounds and doesn't have variable oxidation states. Silver complexes have +1 oxidation state with full 4D subshell, but it is 4D10 in both atoms and ion. It doesn't have partially filled D subshell, and it's not a transition metal. So can't do electron transitions between d orbitals that allow colored compounds to happen. Reactions of halide with silver nitrate in the halogen section. Fluoride doesn't form precipitate. Silver halide precipitate treated with ammonia solution to find different between them if colors look similar. Silver chloride dissolve in dilute ammonia to form complex ions. Silver bromide dissolve in concentrated ammonia to form complex ions. Silver iodide doesn't react with ammonia because it's too insoluble. AgNH32+ is used in Tollens reagent distinguish between aldehyde and ketones, and aldehyde reduce silver in Tollens reagent to silver. Using silver nitrate to work out formulae of chloride containing complexes. Compound has complex, which can have chloride ions as ligands inside complex and chloride ions outside complex attracted ionically to it. If silver nitrate's added to compound, it will form silver chloride precipitate with free chloride ions outside complex. Examples: